Electronegativity, an atom's power to attract electrons. Welcome to this lesson where we'll explore one of the most important concepts in chemistry, electronegativity. This property helps us understand how atoms interact with each other and form chemical bonds. Think of it as a measure of an atom's magnetic pull on electrons when it's bonded to another atom. So what exactly is electronegativity? It's the measure of an atom's ability to attract shared electrons in a chemical bond. When two atoms form a bond, they share electrons between them. But not all atoms share equally. Some atoms have a stronger pull on these shared electrons than others. This pulling power is what we call electronegativity. The more electronegative an atom is, the more strongly it attracts the shared electrons toward itself. Scientists use the Pauling scale to measure electronegativity. This scale ranges from 0.7 to 4.0. Fluorine holds the top spot with a value of 4.0, making it the most electronegative element. At the other end, francium has the lowest value at 0.7. Interestingly, noble gases don't have electronegativity values because they rarely form bonds with other elements. This scale was developed by Linus Pauling and helps us quantify and compare the electron-attracting abilities of different elements. Electronegativity follows predictable trends across the periodic table. As you move from left to right across a period, electronegativity increases. This means elements on the right side of the periodic table attract electrons more strongly. Conversely, as you move down a group from top to bottom, electronegativity decreases. So elements at the top of the periodic table are more electronegative than those at the bottom. These trends help us predict how different elements will behave in chemical reactions. But why do these trends exist? When moving across a period, the nuclear charge increases because there are more protons in the nucleus, while the shielding effect from inner electrons stays relatively similar. This means the outer electrons feel a stronger pull from the nucleus, increasing electronegativity. When moving down a group, the atomic radius increases and the shielding effect grows because there are more electron shells between the nucleus and the outer electrons. This weakens the nucleus's pull on bonding electrons, decreasing electronegativity. Electronegativity helps us predict what type of bond will form between two atoms. We do this by calculating the difference in electronegativity, or delta En, between the two atoms. If delta En is less than 0.4, the bond is nonpolar covalent, meaning electrons are shared equally. If delta En is between 0.4 and 1.7, the bond is polar covalent, where electrons are shared unequally. And if delta En is greater than 1.7, the bond is ionic, where electrons are essentially transferred from one atom to another. Let's look at some real-world examples. In water, H2O, the oxygen-hydrogen bond has a delta En of 1.4, making it polar covalent. This polarity is why water has its unique properties. In sodium chloride, or table salt, the sodium-chlorine bond has a delta En of 2.1, making it ionic. That's why salt dissolves easily in water and conducts electricity when dissolved. Finally, in chlorine gas, Cl2, both atoms are identical, so delta En equals 0.0, creating a perfectly nonpolar covalent bond. Let's review the key takeaways. First, electronegativity measures an atom's ability to attract electrons in chemical bonds. Second, electronegativity increases across periods from left to right and decreases down groups from top to bottom on the periodic table. Finally, electronegativity differences between atoms help us predict bond polarity and understand chemical behavior. Mastering electronegativity is essential for understanding how molecules form and interact in chemistry.
If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.